I want to give one more proof of the characteristic equation because it involves introducing a definition that's useful in planar graphs, and it's a really cool proof as well. And then we'll prove a consequence of it, like a corollary of the characteristic equation as well. All right, so let's restate it again. So the Euler characteristic equation. So if G is a planar embedding, I haven't used this way of writing a graph yet, but like the D-Still book in particular will make a distinction between what's called a graph and what's called a plane graph. Like not a planar, but a plane graph. A plane graph is an embedding of a graph in the plane. So it's the graph together with a drawing. That's a plane graph. You can also call that a planar embedding. So a planar embedding is a graph which is necessarily planar. Non-planar graphs don't have planar embeddings. And it has a planar, like we're given the planar embedding in advance. Okay, so just let that be the planar embedding. Let's see here, with f of G faces, right? Which actually now we know is a fixed constant of the graph. A priori, we don't actually know that when we're trying to prove this theorem, but since we proved it multiple times already, we'll just now say that it's a fixed number of faces. Then we have the following equation, that the number of vertices of G minus the number of edges of G plus the number of faces of G, f of G, always sums to 2. You know, this nice characteristic equation, okay? And this is proof number, I don't know, 7 or something like that, right? There were 3 inductions, and I think we did 3 last time here. And I'm going to start off by defining a notation here that's much more general than this theorem in itself. So it's, I mean, we can use it all the time, but you know, we're going to use it just for the proof here. Okay, so it's something called the dual. So define the dual G star of a planar embedding G. So this is of the planar embedding itself. It's not necessarily of the graph itself. Okay, the dual is only defined on the embedding of a planar graph. Of a planar. Let me even write that out because I really want to emphasize that. Of a planar embedding G as follows. And as is often the case in graph theory, I'll draw a picture as well, which will, you know, crystallize this definition, make it pretty easy here. Okay, so what happens here, when I want to create the dual of G, it's another planar embedding, it's another graph closely related to G as follows. So so each face of G is a vertex of G star, okay? So the vertices of the dual are the faces of G. So obviously we have to have a planar embedding for that first part to make any sense here. And each, okay, we have to be careful here. So the planar embedding often is a multigraph, so I have to be careful with the way I define this here. I'm going to say that, say it this way, 2 vertices of G star are adjacent for each edge on the boundary of the corresponding faces. Let's say on the corresponding faces for each edge on the boundary of the corresponding faces, yeah, in G. Okay, let me illustrate this here. Okay, so we have 2 faces, and each of them has a vertex, and I draw an edge between them if they share a face. So if they share an edge on their boundary, but 2 faces might share multiple edges on their boundary, depending on how the graph looks, and they're going to have an edge for each of those boundaries. So if they have multiple boundaries, they're going to get multiple edges between the 2 of them. So that's what this like adjacent for each means. I mean, this is a little unorthodox. We could say, what you could say is that you introduce an edge between U and V for every edge U and V share on a boundary in the original graph. But let's look at a picture here. This makes it clearer. So let's say we've got this graph here. So in black is G, and it has, here's a planar embedding. And the vertices of G star, actually, it's very easy to figure out how to construct this as well, is just draw a vertex inside of the center of each face here. And I'll put, there's one out here too for the unbounded face. Okay, so I'm going to have 4 vertices in the dual, 1 for each face. And then 2 vertices are joined by an edge if the boundary in G corresponding to them shares an edge. And I do that for each edge that they share. So like the outer face and this triangular face here share one edge there. And the way to do this is actually, if you want to keep the new drawing to be a planar embedding, start from the center of the face, draw a line to the boundary, and then continue that line from the boundary to the next point there. Here I just drew a straight line, but like if you really want to be strict, you can go middle and then back, and you can make sure that you'll get no crossings here. Okay, it's an exercise to prove that the dual is a planar embedding as well, but like it's a little, you know, with an example, it's just like, look, okay, so let's finish it. These two share a boundary as well. These guys share a boundary. And then this face here touches the outside boundary with 2 edges, right? This one here and this one here. So I draw an edge for each. So I draw one there, and then it's joined again to here. But when I want to draw this, I want to make sure I cross the existing face, just for bookkeeping. Ultimately, the graph doesn't change if I draw it like out this way or just duplicate this edge, but it's actually important that the planar embedding be done in this fashion here. Okay, that makes sense. So I made sure to cross the edge that corresponds to this edge here. Okay, and then this one similarly has 2 edges on the boundary. So one goes like this, and the other one goes like this. Oops, the other one goes out here. Okay, I could have, of course, completely ignored the underlying black graph and drawn the blue in different fashion, right? Like from this vertex here, the 2 edges going out, I could have just gone like straight down here, but that just would have complicated matters because it would have crossed these black edges that like it really shouldn't have. I mean, they're independent graphs, but just to keep my picture cleaner here, okay? So maybe we should say something like usually. Okay, so, okay, usually what? Well, notice that each edge of the graph G corresponds to an edge, a blue edge here, okay? There's actually one issue when it doesn't, and let me add to the picture here. What's a situation where maybe an edge doesn't correspond to an edge in the dual, at least not immediately? Anybody see something sort of a degenerate situation here that's a little strange? What if I like add an edge out here? Graph's still planar, it's not connected. Well, like this edge didn't really, it's not a boundary between faces really, or is it? You can think of it as a boundary between the outer face and the outer face, right? It's like, so what kind of edge would this introduce in a dual, according to our definition? What's a reasonable interpretation? Yeah, a loop, exactly, Dakota, right? And like I could even, okay, this is a little much, but should draw it like this too, that it crosses that edge and comes back like that. Like that's a reasonable interpretation, right, of this edge. And actually, it wasn't important that it was disconnected. I could have drawn the edge hanging off here instead, and that would have done the same thing. I'd come, cross it, and go back, okay? So that I want that to be included in the definition as well. Maybe to make, you know, there's more rigorous treatments of this definition here. Right, and actually a strict definition of this maybe should involve topology, right? Just like you could define the edges that way. But I think in this example, this picture here, it's pretty clear what the dual is, okay? And what this means, oh, I don't want that. That now each edge in G has a corresponding edge in G star. That was the importance of introducing this idea for a loop as well. Right, each edge, so observe, although this is a definition, each edge of G has a dual edge in G star. Right, each edge of G is the boundary between 2 faces, maybe not 2 distinct faces. It may be on the boundary of a face with itself. And because of that, that means that I'll always have a blue edge to cross a black edge. Each black edge introduces a blue crossing edge. And that's one of the reasons I emphasize making sure that you draw the blue edge to cross the black edge. that really tells us that this observation makes sense, that there's really a correspondence there, that each black edge introduces a blue edge here, okay? So we can talk about the dual of an edge. And actually that even makes sense, right? Because as an individual graph itself, a single edge would introduce just a loop. It would introduce an edge, it would introduce an edge as well, even on the single graph there. But the thing is, the dual that we construct in this way, it depends on the embedding. This is a nice thought experiment for you. Can you come up with a graph whose dual is different depending on how you embed it? Right, so like you can give me an example of a graph that has multiple embeddings and some of them lead to strictly different duals. It's possible, it's possible. You have to be tricky, but it is possible to do, okay? So yeah, okay, let's say important G star depends on the planar embedding of G. Okay, you can come up with an example of G where you get different planar embeddings and they'll actually give different graphs G star that are non-isomorphic to each other, okay? Not every, I don't know if every graph that you can do that for, but I can come up with examples where you can do it. I think the easiest is to have a graph that's not connected and somehow embed it in a tricky fashion. When it's not embedded, you have a lot of options for how you embed it. Okay, the other thing I want to observe, oh, I guess there's a few observations here. Yeah, let's make a bunch of observations here. So following from this notion of the dual edge, the number of edges in G star is equal to the number of edges in G, right? We get one blue edge for each black edge. We discussed that already, all right? I haven't actually rigorously proved that, but I'm not going to, okay? What else here? G star is planar, and even more than planar, what actually have we arrived at in this drawing? It's a planar embedding, right? It's not only planar, but we actually have drawn it as a planar embedding. And that's actually the easier thing to prove. Like planar is less concrete, or I mean, it's more general, but having a planar embedding implies that it's planar. But that we have a planar embedding, that can be proved by a relatively elementary topology. Just make sure you draw the drawing in the way that I described, where you travel to the black edge and then from the black edge travel to the vertex. And if you're careful and think about this a little bit, you can make sure that that can be done without a crossing. And that follows from the fact that black had no crossings in it there, okay? So I didn't prove that either, but like the usual proof is like, well, look at the picture and like you just could be convinced, you know, but like you can do better than that, okay? And the third property, and this is gonna end up being an exercise, is that what do you think happens if I take the dual of the dual? So if I take this blue graph and repeat the procedure on the blue graph, I get back G. No surprise based on the term dual, right? Usually duals of duals are the original graph themselves. And if we look at this picture, I actually haven't done this, but if you look at this picture and say, okay, if I'm looking at the blue graph, what would its dual be? Well, here's a face. I'd embed a vertex, say the black vertex, into the middle there. Here's a face over here, embed a vertex into the middle. The outer unbounded face, actually, we've got two vertices here, so something's fishy. What am I missing here? I shouldn't have two faces on. Oh, yeah, okay. Yeah, I shouldn't have drawn this edge like this. That was a mistake. This notion, yeah, so if G connected. Yeah, that's important. If G is connected, then the dual of the dual is the original graph. If it's not connected, that's not quite right. So let me actually modify this picture slightly here, just so that we can keep talking about this one. This doesn't change the embedding, but let's suppose that this extra edge I added looked like this instead. So it was connected, but it was still an edge there. And then this blue loop was still okay, right? Because this edge didn't create a new face. It was on the boundary of the outer face still. So the dual was the same here. I just made the edge connected instead. It was a little bit nicer. And then here, I think we're okay because now we only have one vertex on the outer face here. So this would be my vertex on the outer face. This would be the vertex in this picture here. This vertex would be inside this loop here. And then the question is, how would I join them up? Well, the black edges would be, what What's wrong? What's wrong? Something's wrong here. I don't like this edge here. Oh, yeah, here's what's wrong. Okay. Can anybody see what's wrong here? Like with my drawing, like this blue edge is crossing a black edge twice, and this is messing up my notion of dual edge. So what happened is, yeah.
I think we need to,
Van. No, I don't know who's talking to anyone, so.
That edge coming up of like the northwest of that triangle needs to go all the way around town.
Yeah, exactly. This needed to be drawn differently when I did this, right? I drew this edge crossing here before this black edge was introduced, so it really should look like this. It needs to go all the way over here. There we go. Yeah, that's all. Like when I updated the picture, I didn't update the dual correctly. Okay. So yeah, so a few posted in chat here exactly that we get G, and at least in this example, you can quickly check that you do get back G if you follow that rule that you cross where you're supposed to cross, okay? But this is like, these observations all actually should be proved. I mean, I've only given like a hand-waving reason for them to be true. Okay. Yes, and this is important if it's connected, right? If it's not connected, we actually saw an example when this edge was hanging off here. Then we got two black vertices on the outer face of the blue planar embedding, and that's going to look different than the black graph, right? That's going to, like, it had an extra vertex. Okay. All right. So now we have this notion of a dual, of a planar embedding that we can use independent of Euler's characteristic equation, but we're going to use it to prove the Euler characteristic equation. All right. And so I need an additional like definition, I guess. I'm going to put this definition in quotes because this definition is just interior to this proof. We're not going to use this elsewhere here. Okay. All right. So let me check here. Did I change the definition? Yeah. Okay. So, and we'll have to look at a picture here, but a set of edges, say A of G, disconnects. I'm putting this in quotes because, well, you'll see why. Disconnects G star, because this makes no sense, right? A set of edges that are in G, they're not edges in G star. So how can they disconnect G star? Usually we say a vertex or a set of edges disconnect a graph if the removal results in a disconnected graph. But I can't remove edges that are not part of the graph G star, right? The edges of G are not edges of G star, although there's a one-to-one correspondence, right? The edges of A correspond to edges of G star, and that's what I'm talking about here, okay? If the dual edges, let's call them A star, of A disconnect G in the ordinary sense, okay? Okay, so maybe we can like go up here. So, you know, I can attempt to disconnect the blue graph by removing blue edges, right? That's possible. So like, where's a good example here? So say I just want to isolate this single vertex here. I can, isolate this single vertex here. I can do that this is an easy example by removing these three blue edges, right? That would disconnect that edge from that vertex from the rest of the graph. But I could identify these three edges with the corresponding three black edges, right? In this example here, and this will be the observation we're about to make here, what do those three black edges form in G, in the original graph?
A face?
Yeah, they form a face or a cycle more generally. Like, yeah, in this case, they specifically were a face, but actually, as we'll see in a moment, they could be any cycle here, okay? And so it turns out, so observe that a cycle, C, not just a face, but a cycle in G disconnects, so the edges of that cycle disconnects G star as, well, let's look at a picture and then I'll add some words here. So imagine we have a cycle here in the black graph, right? and I remove the edges of this cycle. Not remove the edges of the cycle, but remove the blue edges corresponding to it. So like each of these black edges has a blue edge crossing it in G star, right? And when I say this cycle disconnects G, I'm saying the removal of these edges disconnects G. Why is that? Can anybody see from this picture? How do I know there's vertices in the resulting G minus C star?
We're basically just removing every edge incident to a single vertex.
Yeah, okay, so that's, let me update that slightly. Keep in mind that this is a cycle, they're not necessarily a face. There may be more stuff inside of this face, like additional faces and additional edges, right? Like we could have, like this could look like the interior, for instance. But Van, you're right that inside of this cycle, there's definitely at least one, yes, exactly, Max, right? There's definitely a face inside of this cycle. There may be multiple, but there's definitely a blue vertex inside of here somewhere, for sure. Let me erase this part. So not necessarily one, but definitely at least one. Moreover, there's got to be one on the outside here, right? So there's some vertices in here, some vertices in here, right? Like maybe all of them are in here and all of them are here. And the blue edges go between these two pieces. Removing the blue edges, it's just an edge cut, right? That just identifies an edge cut. Like it definitely disconnects this part from this part here, okay? And why is that? Well, it's actually by the Jordan curve theorem. This cycle here splits the plane up into two regions, the interior and the exterior. And the interior faces are vertices of G star, and the exterior faces, exterior to the circle, are faces of vertices of V star. Yeah, hold on. Are faces of G star, and the edges between them have to cross this Jordan curve. And I've deleted all the edges that cross it. So I made a cut there, okay? Yeah, Van asks, is there a one-to-one correspondence between cycles in G and boundary in G star? No, right, no. So like look up here, right? This 4 cycle here is not a face, right? So that's what I'm getting at. Like this face here, I mean this cycle here, removing the edges, the blue edges that cross that also disconnects the graph, but that's not actually a face, right? There's 2 faces interior to it, but it's not a face, right? So every face is a cycle, not every cycle is a face. But every cycle contains faces interior to it. Either it's a face itself or somewhere smaller inside of it has to be a face. So like removing this red cycle, and when I say remove, I'm not removing a cycle. I'm creating, the cycle is a boundary between interior faces and exterior faces. And if I remove the blue edges crossing that boundary, it disconnects the graph, okay? So that's, yeah, disconnects G as well by the picture, but maybe we can say there are vertices of G star inside C, right? Then you can just think of C as a curve in the plane. Forget it's edges of a different graph, but it also represents a closed curve in the plane. So there are vertices of G star inside C and outside C, and all edges of G star that cross C are removed. Okay, so G star minus C star is disconnected. So a cycle in G corresponds to a cut in G star, right? C star is these blue edges, right? These blue edges are members of C star, and in black is C. Okay, what are the dual edges for the cycle C? They're these blue crossing edges. They form a cut. Okay. And the reverse is true as well, meaning if I give you a set of edges that does not contain a cycle, yeah, so by the way, so a cycle disconnects G, and any subset of edges of G that contains a cycle will obviously disconnect G, the dual as well, right? All I need is a cycle among my edges, then they disconnect. Because a cut plus some edges is still a cut, okay? But on the other hand, let me change colors here. An acyclic graph. I don't think I've used this term here, but this is a graph that contains no cycle, okay? Actually, we have a term for this. What's an acyclic graph? We have a different word for this.
Tree.
Almost, right, Christian? A tree is a connected acyclic graph. So acyclic's a little more general than that. right?
Would it be forest?
Yeah, forest actually, right? Forest has no cycle and its components are trees, right? We've used the term forest, right? Haven't we? I hope so.
Yes.
The forest is a connected acyclic graph. No, is an acyclic graph, not necessarily connected. A connected acyclic graph is a tree necessarily, or a connected forest is necessarily a tree. Okay, so I don't know. In some contexts, we like to say acyclic just because it emphasizes the lack of cycles. Actually, typically I prefer forest, but anyway, you know, what's important isn't that the components are trees. What's important is that there aren't cycles. Okay, so an acyclic graph. Let's even say in acyclic graphs, subgraphs, edges in G. So what I'm saying is if I take a set of edges in G that are not forming a cycle, that don't form a cycle, then let's say for edges A, let's call them A. A star is not an edge cut of G star. Okay, so if I let's look at the example here. I don't know if I identified a good set here, but we saw that if I remove a set of edges that contains a cycle, it splits some vertices from other vertices of G star, right? It creates an impassable boundary. But if the edges that I remove don't form a cycle, let me maybe do this in green. So say I remove this edge, this edge, this edge, and this edge or something, right? So green doesn't form a cycle. This actually cannot disconnect the graph, okay? And the reason for that is there's no boundary. Like this vertex here can get to every other vertex because it can just avoid the green edges somehow. There's a UV path for every pair of vertices UV that you can form by just avoiding green edges, right? Just avoiding that green wall. The green wall is not enough to set vertices off from each other, okay? Again, not a rigorous proof, and I don't intend to be more rigorous than that. Getting some of the details right in these things requires a deeper dive into topology that I'm willing to take, but it's pretty evident, right? Like you create this like wall, but not a closed wall. I can get from U to V. They're not separated from each other. There do exist blue edges that cross black edges that weren't removed yet, okay? Oops, okay. Yeah, so I mean, that's the end of that argument. I'm not giving the full argument there. So what that means is, so edges A with cycles in G correspond to an edge cut A star in G star, and vice versa. So if I give you an edge cut of A star, of G star, then that necessarily contains a cycle among the edges of A, right? The dual of the dual is the original graph. So I can run this backwards here. If I give you an edge cut well, no, it's not because of the dual. The dual, it's just because of the if and only if. Cycles or graphs that contain cycles correspond to cuts, and acyclic graphs don't correspond to cuts. So if I have an edge cut, it had to come from a cycle or something that contained a cycle. So there's a correspondence between there. So if I talk about an edge cut in A that's A star of my dual, I can go back and say, oh yeah, there's a cycle among the dual edges, right? The dual of the dual does produce give you back A, okay? And so this is the fact that we're going to use this information here. This is very important here to prove the Euler characteristic equation now. And this proof is amazing. Okay. So now, let's say that let G be a planar embedding with f of G faces. Okay, and let G star be its dual. Okay, the dual of that thing there. Okay, so let's look at a spanning tree T of G. Okay, the spanning tree T of G, so T is connected, not that important yet, and acyclic. right? So what does that tell you about if I remove t, or the dual of t, from the dual of g? So I take g star and remove from it the dual of t. What information do you know about this graph? Because t is acyclic, it forms an...
Connected.
Yes, exactly. So this graph is connected, right? It's still connected, okay? But, yeah, dual edges, yeah. So let's say as t star not a cut, say, just to re-emphasize, right? If t is acyclic, then t star is not a cut in g star. So g star minus t star remains connected because t doesn't contain a cycle in it. Okay. Now, moreover, now this is interesting, and this takes a little bit of thought here. T is connected. Okay. What if I look at the dual of these edges, g star minus t star? So the dual of these edges. Okay. So I remove t star from g star, and what I'm left with here, this is still planar, right? And it's connected, right? What happens if I look at the dual of this graph here? What is the dual of this graph? This is the complement. Okay, let me not say anything here. So I arrived at this by removing the dual edges of t from g. What is the dual of this thing here? So in other words, what is the dual? What is this guy here? Okay, go ahead, Ethan.
Does that become G minus T?
Yes, it does become G minus T. Actually, that's not even what quite I need to observe there, but that is actually G minus T. It's a little bit confusing, but it turns out that, maybe I should have said this here, that G star minus T star is the same as G minus T star. Okay, you can think about this for a little while, but why is this true? I just remove T from G and then take the dual. That's actually what I usually do here, right? When I say, is that, yeah, I mean, okay, that does require a little bit of a proof there, but I don't even need this fact here and this fact here. So what I wanted to say is, so this, okay, I'm going to put this in parentheses because I'm kind of making the wrong observation. Now consider what I want to do is the set of edges. So this, what's in parentheses, also leads to the argument. I just want to rephrase it a little bit, of G star minus T star. So if I think of this as a set of edges, it's a connected set of edges. And these ones, let's ask the question, do they disconnect G? Right? I could take in parentheses, in quotes here, right? So do the dual edges corresponding to these guys disconnect G? The dual edges of these edges are what edges? Actually, Ethan did point it out. They're these edges here. When I remove these edges, what graph am I left with? If I remove G minus T from G, I'm left with T. But T, what do we know about T? We use one property, that it's acyclic. Its other properties that it's connected. So T is connected. So what does that tell you about these edges here? So this means that this does not disconnect G because it results in a graph that's still connected, right? So it means that this set of edges here is not a cut, right? Removing G minus T leaves a spanning tree, so it's not a cut of the graph. And if the dual is not a cut, then the original, which is this thing here, is what? It's acyclic. Okay. So G star minus T star had to be acyclic. And now we're almost done with the proof here. The final observation is this graph here is acyclic and it's connected. We already arrived at it being connected. So G star minus T star is a spanning tree of G star. It's connected and acyclic. It necessarily includes all vertices. We never removed vertices. Everything was an edge cut. So this is a spanning tree of this. And now the final step is to observe the following. How many edges are in G? Well, there's obviously as many edges in G as, let's say, E of G, E of T plus E of G minus T, right? But this is the same as the number of edges in T plus the number of edges in G star minus T star, right? All I removed was the dual edges. There's a one-to-one correspondence between edges and dual edges. And now, here's the best part. T is a spanning tree of the original graph G. Spanning trees have one less edge than vertex. So this thing here, by the fact that that's a spanning tree of the original graph, this has V of G minus 1 edges, okay? This, we argued, G star minus T star is a spanning tree of G star. So this should be the number of vertices of this dual graph minus 1, right? Number of vertices of the dual graph, right? Let me put it here, V of G star minus T, sorry, shoot, T star minus 1, right? That's the number of edges of a spanning tree of G star minus T star. But how many vertices are in the dual?
One for each face.
Yeah, one for each face. So this is actually F of G. We can translate this to F of G. So it has one less edge than the number of faces of the original graph, because the dual has as many vertices as faces in the original graph. And now look what we have. We have edges equal vertices minus 1 plus faces minus 1. If you simplify, then you get V of G minus E of G plus F of G equals, there's two 2's left over on the opposite side. Isn't that awesome? That's like so cool, man. Yeah, it's a little subtle. When you get more and more comfortable with, yeah, exactly, Dakota. It's as you get more and more comfortable with the dual, this proof can be basically argued in like one sentence. Like when you're really comfortable with the dual, then like all these notions, like Ethan pointed out here, like these and so they become instantaneous with a little bit of thought. And like that one and this one here don't require any thought after a while of being familiar with these. And then really you can just say that actually the acyclic property and the connectivity or remaining connectivity, the cut, it's maybe cycles and cuts are like duals of each other. And just using that observation immediately leads like basically to this sentence here. And yeah, you just get like, because faces turn to vertices, you get your answer there. Okay, so yeah, that's just an awesome proof. Okay, let me finish with an important corollary. And I don't know where the notes are, but oh, maybe it's here. I mean, we don't really need notes for this. This is pretty easy here. Okay, so I'm gonna call this a theorem, but it's a direct corollary of the Euler characteristic equation. And in the notes, I've called it the planar edge bound. Okay, so something intuitive that makes some reasonable sense is planar graphs can't have too many edges. Like when you add more and more and more and more edges, you increase the likelihood that it's going to be hard to draw it, right? Like it just seems intuitively reasonable. Like if I gave you, we already know that the complete graph on 5 vertices is not planar. Now, if I have 100 vertices and 10 edges, yeah, you're probably going to be able to make it planar unless it contains a K5 inside of it somewhere. But yeah, if you just keep adding edges, at some point, at least in practice, you're going to run into trouble. But we should actually prove something concrete. Okay, and we should find a bound on the number of edges, and we can get such a thing. So if G is planar, let's say it's on at least 3 vertices, then the number of edges of G is bounded above by 3 times n minus 6 in a planar graph. Okay. Okay, so two things. First thing, this is not only an edge bound, it's very sparse. What sparse mean? Has few edges, right? How dense can a graph be? Graphs can have up to order n squared many edges, right? Like n choose 2 is the maximum number of edges you can have without multigraphs, and yeah, that's quadratic, right? In n, this is linear in n, right? So this says like you don't have that many edges compared to the total here. Yeah, by the way, this graph has to be simple. Obviously, when we talk about number of edges in a multigraph, it's not an interesting question because you can have infinitely many edges in a planar multigraph, right? And you just keep doing this. Like that's obviously the thing we shouldn't talk about, right? I can just keep adding edges here. So yeah, it's a like simple planar graph. Usually, like I've said, the graphs are simple unless otherwise specified, but maybe it's worth stating here. Okay. The other thing, you don't need to require that the graph is connected, but in the proof, we will assume it's connected, okay? So without loss of generality, suppose G is connected. I think we need this in the proof. If the graph has multiple components, this bound can be improved. And maybe that's something I'll ask you guys to do here, just improve by a little bit. But the point is, if the graph is not connected, I can add edges to it and connect the pieces, and that will only increase the number of edges there. And so if I assume it's connected, that'll be an upper bound on the number of edges in any planar graph. If I have a planar graph that's not connected, you can always safely add an edge to it and not create a crossing, right? Like literally take the outer face of each of these, which is a Jordan curve. They don't intersect each other. There's some way to travel from here to here without making a crossing. Just give it some thought, right? So I can assume it's connected by adding edges. So if I can prove this for connected graphs, I prove it for all. Okay, so suppose G has, let's just say, suppose G is a planar embedding. So take a planar embedding of it. We know that in a planar embedding, the number of faces is fixed. So we can talk about the number of faces, number of vertices, and so on. And then we're going to do the following. Count the edges of G face by face. What do I mean by that? For each face of the graph, just count the number of edges on its boundary, okay? So each face. Okay, so what you're actually doing is creating a sum. Like sometimes we write it like this, F is a face, and the cardinality of the face is the number of edges on that face there. Each face is actually isn't necessarily a cycle. Maybe I've been a little careless stating that. Like this, the outer face here is not bounded by a cycle. So cycle plus this edge here is possible. But that's not that important here. So each face is composed of a number of edges, right? How many edges are on a face? At least when n is at least 3. Actually, I guess, what do I need here? Maybe there is a bit of an issue. We'll think about that as we go through here. So, oh, I thought it froze for a second there. Yeah, I'm going to erase the sum here. You can argue it with this here, but this is throwing me off. Okay, so let's just imagine a more typical scenario here. Do this as an example here. Here's a graph with 4 faces. I'm going to go face by face and sum up the boundary. So I get a contribution of 4, 3, 3, and the outer face is 1, 2, 3, 4, 5, 6. That's my contribution if I count edges in that way. Okay? But each face then contributes at least 3 edges, right? What's the smallest face you can ever have? Like a triangle is the smallest face that you can have. Actually, there is one problematic scenario. This is what's bothering me here. is here's a 3 vertex graph that is planar, that has one face only, and it has 2 edges on its boundary. This is a little, this one's, I don't know, actually know how to deal with this. I'm probably we can add something in the theorem, or maybe it still holds for this. We can check at the end here.
I guess you could. I'm not sure what assumption you would make to imply the addition of the additional edge there to make it a triangle.
Yeah. So actually, Ethan, we can actually do this too. You know what? Maybe let's add this. That's actually makes things easier. It just kind of, it doesn't work in the generalization that you guys will have to deal with later, but it's okay. So moreover, we can not only suppose it's connected, we can suppose it's maximal, right? Like we know what maximal planar graphs look like. Every face is a triangle. So we actually get something even stronger. But like if I can maximize a graph by just adding chords when they're not there, just adding edges when possible. So we can even say maximal if we want. And then if we know it's maximal, then every face has at least actually exactly 3 edges on it. But you don't have this weird like hanging business here, right? And every face is enclosed by a cycle. Certainly we can assume it's maximal. If we can prove an edge upper bound on a maximal planar graph, then we prove it for all that are not maximal, because maximal meant edge maximal. Well, that's one way to get around it. Yeah, so each face contributes then at least 3 edges, actually exactly 3 edges in a maximal example, but at least 3 edges. And each edge is counted. How many times is each edge counted in this procedure, especially in this example here?
Twice.
Twice, once for each boundary, right? That edge is counted by the 4 here and by the 3 here. Okay. So that means that the number of edges in G is at least as large as 3 over 2 times F. Each face contributes at least 3 and is counted at most twice. Okay, so we're dividing by it's clearly a lower bound on the number of edges here. And now the proof is just some arithmetic here. Now we just use the Euler characteristic equation. Let me just rewrite this here. So this is an upper bound on F. F is at most 2/3 the number of edges in G. And then Euler characteristic says n minus m plus f equals 2, which can be written as n minus 2 plus f equals m. M is the number of edges of G. Wait, that's not what I want. I don't want to write this. Let's maybe solve for f. Actually, it doesn't matter. So let's take n minus 2 equals m minus f, say. Yeah, why do I write it like this? How about m? Like, we're just plugging in and solving. I'm just trying to come up with the cleanest way to do it. Like, it's not hard here, but we want to know a bound on, oh, you know what? I don't want to solve for m either. Okay, let's like literally just plug in. N minus m. Instead of f, I'm going to replace f with 2/3 m, right? M is the number of edges. And then let's get the inequality in the correct direction here. I've replaced f with something smaller than f. So the left-hand side is bounded above by 2, right? I replaced f with a smaller number there. And then I've got n minus 2. Oh yeah, no, I know what did that. Is at most 1/3 m. Nope, see, I did something wrong, didn't I? What is going on? It's kind of embarrassing. I mean, I'm not actually embarrassed, but so I'm just gonna stop here. These two imply it's literally just algebra that E of G is bounded above by 3n minus 6. Okay.
I think your initial inequality where you say the number of edges is at least 3 over 2f might be backwards.
This one here, is this backwards? Is it backwards? So each face contributes at least 3. So the minimum it could contribute is 3. And then dividing by 2 is even worse because some edges might only be counted once. Like if you have an edge like this, it actually only gets counted once, right? So I think this is a lower bound on the number of edges. I definitely have more edges than this guy here. Did I flip this guy around here? So I replaced, yeah, I did, sorry. here, when I plug this in here, I replaced f with something larger than f, not smaller than f, right? F is bounded above by this guy here, right? So I replace f with something larger. So this inequality here is this direction. Yeah. Man, you know how many times this has gotten me in my career that I flipped an inequality in this very specific thing? I have this I have the yips when it comes to this thing here. So, all right, and now we got it, right? Now we multiply both sides. So m is at most 3n minus 6. Voila. That's the end of the proof. Okay. I'll just add one parting word here. This count relied on the fact that each face had 3 edges on it, or at least 3 edges on it. If I told you, hey, your graph doesn't have any triangles and it's planar, this can be improved, because you can say, oh, then every face has at least 4 edges on it and you get a better bound somehow. That's going to be what turns out to be pretty easy, but homework exercise. So if you have a planar graph and you say it doesn't have short cycles, all the cycles are of length 100 or longer, then you get increasingly better bounds on the max number of edges. But that also makes sense, right? Because think about density in your graph. And when I say density, I mean number of edges. If I say, hey, your graph doesn't have short cycles, then like locally, it doesn't have a lot of edges, right? Because like if I say there's no cycles of length 100 or shorter, then if I look at 100 vertices, there's no cycle among 100 vertices ever. So among 100 vertices, you always see forests. You always see acyclic graphs, and those have few edges, okay? This is a fact we'll return to later. But let's stop there since I've kept you guys over.